Hello, I'm Melissa. I'm a graduate student at Oregon State University. I'm working with my fellow graduate student, Faiza, and Dr. Weiss and Dr. Ishker, my advisors, on a clinker-free binder for concrete. We decided to start with sodium silicate in the form of water glass. The water glass we're using is 81% sodium silicate and 19% water and in powder form. Our theory is that sodium silicate can provide the foundation for a clinker-free binder. And to test this theory, we're looking at the Pozolonic potential and reaction products using the Pozolonic reactivity test, thermogravimetric analysis, and thermodynamic modeling. The Pozolonic reactivity test is designed to determine a numerical value of reactivity for supplementary cementitious materials, or SCMs. The SCM is reacted with an excess of calcium hydroxide and a 0.5 molar potassium hydroxide solution for 10 days. The consumption of CH is measured by finding the remaining CH using thermogravimetric analysis, and the heat release is measured using isothermal calorimetry, and then a degree of reactivity, or DOR star, is calculated. The results of heat release in joules per gram SCM and CH consumed in grams per 100 grams SCM are plotted on the graph with reference to the ideal aluminum oxide and silicon oxide degree of reactivity lines. These reference lines are connected to indicate different DOR star values, and DOR star can be calculated with this given equation for each material, with the C's being constants. The isothermal calorimetry results show just how quickly sodium silicate reacts, with most heat release happening within the first 6 hours. At equilibrium, sodium silicate produces 515 joules per gram SCM, and silica fume was slightly higher with 595 joules per gram. The curve of sodium silicate is actually preliminary data at this point. The heat release happens so quickly that this line is composed of a couple of sets of data, with some data being from samples mixed inside the IC and others being mixed outside and then placed in after mixing. More research is needed on what's happening with internal mixing to verify these results, but we're pretty confident with these preliminary ones. The TGA graph of sodium silicate also shows a very quick reaction, with the majority of the CH consumption happening within the first day, where the silica fume is seen to continuously increase its CH consumption over the course of 10 days. Sodium silicate consumes about 91 grams CH per 100 grams SCM, and silica fume consumes about 141. We are using the highest value of CH consumed for the sodium silicate, even though the values drop off slightly moving towards the 10-day reading. Our theory is that the Pozolonic reaction is so quick that we're possibly losing the KOH buffer within the test, which is affecting these results. When calculating and plotting our results on the PRT graph, the sodium silicate shows a 70.3% degree of reactivity compared to silica fume at 78.1%. These results are somewhat close, and the difference in degree of reactivity can possibly be explained by the silica fume being significantly more fine than sodium silicate. Another important component of creating a binder for concrete is the creation of calcium silicate hydrates, or CSH. This can be conceptualized using GEMS thermodynamic modeling. The model suggests that the system produces complex form of CSH, labeled here as CSHQ on this graph, which we will not go into further details here about, but as can be seen on this plot, as the water glass to calcium hydroxide ratio increases, the CSH content does as well in a very linear-like fashion. The CH consumption also increases as well. Since the CH remaining decreases, that means the consumption is increasing. We can use these models to help create a mix design to test experimentally. But a keen eye might notice that the thermodynamic model here does not quite match the PRT test results. Our water glass to CH ratio for the PRT is about 0.33, and in the graph, it only shows about 10 grams per 100 grams SCM being consumed, where the PRT showed 90. This could be in part due to the difference in temperature. The PRT is ran at 50 degrees Celsius and modeling is done at room temperature. The model was also ran with a different KOH molarity and a different pH. We plan on exploring the reasoning why this is happening more in depth in the future. To experimentally back up the thermodynamic modeling, we created a paste using water glass, calcium hydroxide, and potassium hydroxide solution using the same ratios as in the model. We then cured it at 50 degrees Celsius in an oven, or for 7 days, then stored at room temperature until we ground it into a fine powder. Oven dried it for 24 hours at 100 degrees Celsius to remove the water, and then ran it through the TGA. This graph shows the weight loss curve and its derivative here. If we focus just on the derivative and then overlay the derivative weight loss graphs of the initial calcium hydroxide and initial water glass amounts, it is clear that there are reactions taking place. Looking here, you can see the large amount consumed between the initial CH and the CH consumption, or the final CH. The loss of mass here is closer to that seen in the PRT calculations and supports those numbers as well. We can also take the derivative curve and deconvolute the peaks to see the decompositions more clearly. For this graph, the cumulative peak fit curve has an R² value of 0.997 when compared to the original, which is a pretty close fit. Looking at the individual curves, this one is going to indicate the remaining unreacted water glass in the system. The area under the curve correlates to % weight loss, or the grams per 100 grams binder remaining in the system. This system started with 79 grams of water glass per 100 grams and is now down to 5.67. This curve here shows unreacted calcium hydroxide with 1.33 grams of the 21 grams remaining. The last two peaks are the most exciting peaks. This one indicates the presence of CSH. The Kassenberg et al. In 2009 found that the initial loss of water from CSH can be seen in a TGA data from 110 to 170 degrees Celsius. While this curve peak is at a slightly higher temperature, this is most likely due to the complexity of the CSH in the system. The last peak also indicates CSH formation. The same reference found that the bound water of CSH is released between 180 and 350 degrees Celsius. The Pozolonic reactivity and CSH production show that the sodium silicate has potential to be used as a clinker-free binder. There's a lot more to learn about this system, but we're moving forward with testing, exploring different additions and mixed designs to optimize a binder. I want to conclude with a special thank you to the ACI Foundation, Barbara and Calvin McCall, and the Carolinas ACI chapter for the fellowship that helps alleviate financial stress and affords me the opportunity to better focus on my research. And thank you to everybody here for listening. Thank you to Dr. Weiss and Dr. Ishker for their guidance. If you have any questions or comments, please feel free to email me or reach out to me on LinkedIn.